We know that light, being an electromagnetic wave, sometimes behaves as a particle. Actually, any particle sometimes behaves as a wave also. This can be surprising because it even means that us people, we are particles, we are matter, and we should also be having this property of behaving like both a wave and a particle at the same time. Um, it is because of a law, the principle, the equation that lambda is equals to Planck's constant and inversely proportional to the momentum that we people, as we have more mass, we are we have a smaller momentum, which we are inversely proportional to lambda, and that is the very reason why we have a smaller mass, smaller properties of wave, and that's why we as people do not behave like waves a lot, but we also have this property as anything does. And the first to have this idea of a wave behaving like a particle and a particle behaving like a wave was Louis Victor de Voigt back in 1923 when he was writing a thesis for a doctor's degree at the University of Paris. Actually, at first, he wasn't taken seriously, and they didn't even wanted to give him the degree because the idea sounded crazy itself, and it was only thanks to Albert Einstein, that was occasionally visiting Paris at the time, that he could get his degree, because Einstein heard the idea and he thought that perhaps it was probable, it could be true, and it wasn't so crazy as it first sounded to them. It was until 4 years later that C.J. Davisson and L.H. Germer in New York City made an experiment which happened to prove the hypothesis that Boyle had made at the beginning. We know that waves can be diffracted, but if you shoot particles at something, there will always be a shadow. An example of this is on the modern electron microscope. Um, let's say if you spray it with electrons, this is a microscope, and then you spray it with electrons, a beam of electrons, the lamp will spread the beams out like this. And then you let them hit the screen, and you'll get an enlarged shadow of the thing right here in the screen, because all particles are meant to leave always this shadow when they are shot at something. Here the particles that make up smoke look like the shadows of little blocks, but the edges of the shadows don't look sharp. There is light and dark bands in them. The electrons here show a case of diffraction of particles. The electrons are behaving like waves. This suggests that if we want to look for the wave-like properties of matter, we might shoot a beam of matter at a grinding and see how the matter bounces back. If it bounces back every which way, then that's just what we expect from particles. But if it bounces back in beams, then the particles are behaving like waves. We need a grating with lines whose spacing is comparable with the wavelength we are looking for. But what wavelength are we looking for? To answer this question, we go back to Boyle's hypothesis. He stated that if the momentum was equal to Planck's constant divided by lambda, then separating lambda in this equation, we would get that the wavelength would be Planck's constant divided by the momentum. And here, we need a wavelength long enough to deal with. I mean, in the experiment we are looking forward to make to prove our hypothesis. And for this to be something we can deal with, this inversely proportional must be a very small value. So we're looking for a very small momentum. This is actually sometimes called the Boyle relation. And if we put numbers in it so that we can get an approximate value, we know that here the constant it's 10 to the negative 33. I'm sorry for that 3. And the value we're looking forward to put here at the bottom needs to be a very small momentum. So if we get the mass of an electron, one of the possible momentums that we can get, I'm not really gonna get into that procedure here, but the value that we get is 10 to the negative 23. And if we divide this, we get that lambda is equal to 10 to the negative 10 meters, which is about the size of an atom. So we need a grating with a diameter about the size of an atom. And this is actually kind of hard because everything is made up of atoms. Here I'll build a diagram of the experimental setup used by Davisson and Germer. It consisted of a nickel chloride crystal, which is the main target, an electron gun G, and a detector. The gun produces a beam of electrons, so the electron gun they used consisted of a tungsten filament F and high and low tension batteries. The low tension battery was used to heat the filament, then this one produced an electron beam. A high tension battery was provided to accelerate the electron beam. The detector moved on a circular scale, and a sensitive galvanometer was also connected to the detector. And then here's how the experiment was performed. The electron beam was made to pass through a pinhole and made to strike the crystal. The electrons scattered in all directions, acting like waves. They also observed that at certain angles, the detector indicated a peak in the intensity of the scattered electron beam. This maximum intensity was due to constructive interference, a phenomenon confined only to waves, so they proved the wave nature of electrons. Davisson and Germer plotted a graph, taking the angle between the incident and scattered direction of the electron beam and the intensity of the scattered beam at different values of accelerated potentials. From the experimental curves obtained, the following conclusions were drawn. 1. Intensity of scattering depends upon the angle of scattering phi. 2. A bump or kink always occurs in the curve when phi equals 50 degrees. 3. This bump or kink increases as the accelerating potential difference is increased. And 4. At 54, this bump is maximum and then it decreases on further increase of potential difference. This peak indicated the wave behavior of the electrons. And thus, the Davisson-Germer experiment proves Boyle's hypothesis of the wave nature of matter particles.